Yes. Okay.
All right, so hi everyone, I'm Oliver Long, a PhD student at the University of Southampton, and I'm here to talk about self-force in hyperbolic binary black hole encounters, and this is work I've done with my supervisor, Leo Barak. So first I'm going to talk about EMRIs, or extreme mass ratio in spirals, and these are compact objects which orbit a supermassive black hole that have mass ratios less than about 10 to the minus 4. And an orbit of 1 is given on the right. Now, because we have such a natural small parameter in the system, what we can do to model these is expand in this small parameter. So here on the left hand side, we have the full two-body metric of the system. We can expand this as the 0th order with the Schwarzschild or Kerr metric of the big black hole. Then we have these H1 and 2, which are metric perturbations which take into account the mass of the small black hole. So we can detect the gravitational waves from these bound systems, such as with the future LISA detector. Now, first order corrections are sufficient for detection, but we will need second order corrections for parameter estimation. Now, these are for bound orbits, and I'm going to be talking about scatter orbits. So why are these interesting? Well, if we look on the right, we have the parameter space of the two-body problem. Up here at the top, we have weak field approximations. Down in the right, we have self-force, which is what I do, and then we also have the full numerical relativity in the bottom left. So it was shown by Demore recently that we can use data from the self-force region to get information in the weak field. So if we have first order self-force scattering data, we can get up to 4 pm. And similarly, if we have second order data, we can get up to 6 pm, which is higher than we've ever gone before. We can also use self-force scattering data for calibration of effective one-body models for bound orbits. So if we look at the new plot, we have periastron against impact parameter. You can see that even for relatively low energies, such as E of 1.1, that the small object dips well below the innermost stable circular orbit. So we are very much within the strong field regime. Another thing we can do is compare with scatter amplitude calculations, such as done with quantum or effective field theories. So these calculations are done obviously using very different techniques to what we use within GR. So comparing them is something that would be very interesting. Now I'm going to move on to talk about the scatter orbits themselves. So one way we can parameterize them is with energy and angular momentum. And for a scatter orbit, the energy E has to be greater than 1, and the angular momentum has to be greater than a critical value of n for a given E. Otherwise, the particle will plunge into the big black hole, and that's not the type of orbit we want. Another parameterization we can use is velocity at infinity impact parameter, and we have a graphical representation of impact parameter here. Now, for the geodesic case, we have 3 ODEs in proper time, and the thing to notice about these is you have the constants E and L. If we now add in the self-force corrections, what we have is E and L, instead of being constant, and now varying with time. So we have the geodesic values, and then we have integrals of the self-force over the previous orbit. And these Ft and Fi are the time and azimuthal components of the self-force. What we want to look at in this work is the scatter angle. So this is defined by this equation here, or graphically also here. Now, if we look at the integrand of the equation, this is just a function of E and L. So what we can do is we can substitute in the time varying E and L from the previous slide, and we get something of this form. So we have the 0th order, which is just the geodesic result, and then we have this first order correction. Now, we have done this and gone through the calculation, and after lots of simplifications, we get something of this form. So you can see is an integral over the entire orbit of the particle with the self-force components, and then also these G's, which we have calculated analytically, and these are just functions of the geodesic values of E, L, and then time. So we want to test this equation, and we're going to do that with the scalar self-force. So to calculate the scalar self-force, we use a scalar field decomposition in terms of the spherical harmonics Y. and then we get this time radial field lowercase psi. This obeys a 1 + 1D scalar wave equation. And if we look at the form, it has a principal mixed part, a potential term, and then a source term, which is proportional to a delta function along the orbit. And we've written this in null Eddington-Finkelstein coordinates, which are coordinates on the light cone. So we solve this numerically on a double null grid, and we set up this null grid on the light cone. So we split it up into a grid of U and V. So we have initial conditions on the initial rays of U and V, and then we solve a finite difference version of this wave equation iteratively along the grid and get the values for the scalar field. So once we've done that, we need to get the scalar self-force. Now, the definition for the scalar self-force is same as the gravitational with the E and L's here, except now we have this different small parameter, which is the scalar charge Q squared over the product of the masses in the system. So to get the scalar self-force, first we define this F tilde, which is simply just the derivative of the scalar field along the orbit. From that, what we can do is take the projection orthonormal to the 4 velocity of the orbit, and that is how we get the self-force here, this F. So we did this for the sample orbit shown here, and we chose this orbit simply because, as you can see, it's fairly in the strong field regime as it's dipping quite far below the ISCO, and it also has a fairly sizable scatter angle. So this is the result that we got for the time component. You can see here that there is a peak about periastron at t = 0. And also, if you look closely, you can see the peak isn't exactly on the periastron, it's actually slightly delayed. Another thing you can see, if you look at the inset, which is the same data scaled by r³, you can see that there are these waves, which I'll explain in a second. If we look at the F₃ component, you can again see there's the peak at periastron, the slight delay, and the waves are even more prominent here. So what these waves are they're quasi-normal mode excitations of the big black hole. So these are similar to the ring down excitations that you see in the LIGO waveforms for binary black hole collisions. Next, we want to move on to actually looking at the scatter angle. And we did this for a variety of orbits. The orbits we chose, we kept the velocity constant at 0.2 and then changed the impact parameter. You can see as we decrease the impact parameter closer to the critical value, that the orbits get closer to the central black hole, and also the scatter angle increases. So we calculated this correction, and what we have shown in the main plot is the ratio of the two terms in this equation, ignoring the factor of eta. You can see as we get closer to the critical value that this ratio blows up, so the correction is becoming more significant. But one thing we need to remember is that this eta is much less than 1 still, so they're not becoming comparable. If we look at this inset, this is just the first order correction scaled by b². You can see that this is decaying as we go away from the critical value towards this red line. Now, this red line is a weak field value of the correction as calculated by Gralla and Lobo. This is something we want to compare to in the future, but unfortunately our code cannot get to the weak field at the moment. So moving on to outlook, the first thing we want to do is to extend our numerical calculations to be able to compare with that red line we saw on the previous plot. We then want to perform the first calculation of the gravitational self-force run by an orbit, as that's the physically relevant one. And myself and my supervisor have done intermediate calculations of this, but we just need to finish them off. We want to then use that data to calculate the gravitational self-force correction to the scatter angle, and then apply it to the applications that I spoke about in the motivation. And then finally, we want to extend our model to have a spinning primary, so the Kerr metric, and then add second order self-force effects. Thank you.
Thanks very much, Oliver. There are no questions from the audience just yet, so I will start by asking what might be a slightly naive question. which is you mostly talked about this from the perspective of Lisa, but
Yep.
do you expect that these kinds of events would be observable in advanced LIGO data as well, or is it really just something for the Lisa regime?
No, it's really just, I'm sure the people following me will explain this in more detail as they do bound orbits, but no, the frequencies that MREs produce are very much in the Lisa range and not in the LIGO range.
Sure. Okay. Thanks very much. There are no other questions yet from the audience. So if anybody does have a question for Oliver, please do feel free to ask it in the Slack channel. But in the interest of time, let's move on. So next up,